Welcome to our today's revision. As we get closer to exams, it's important you attempt recent papers. In today's papers, we want to look at May-June 2025, paper 4.1. We want to answer question number 1, which has to do with gravitational field. Gravitational potential at a point is work done per unit mass in taking it from infinity to the point of reference. B. Mars is a planet that may be considered to be an isolated uniform sphere of radius 3.4 times 10 to the power 6 meters. A satellite of mass 122 kg is in orbit around Mars at a constant height of 1.7 times 10 to the power 6 meters above the surface of the planet. The height of the orbit is increased to 6.8 times 10 to the power 6 meters above the surface. This increases the gravitational potential energy of the satellite by 5.1 times 10 raised to the power of 8 joule. Show that the mass is 6.4 times 10 raised to the power of 23 kilogram. It's important for you to know that gravitational potential energy is work done on a mass in bringing it from infinity to a point of reference. So work done is basically force times the distance, and this will give you gravitational force is gmm over r squared times that distance. This give you gmm over r. It is given to us that the mass and the others, the second mass has is a radius and is moved above it. So this r stand for this. The radius that is mentioned is here. From this point down is what we talk of height above. By implication, the distance between the two, in which we call separation, will be the radius of Mars plus the height. Take note of that. If we want to find the gravitational potential energy for when the height was 1.7 times 10 raised to the power of 6, we will use this 1.7 and this 3.4. Let's write for the first one there. This will give us gmm over r1, which is g is 6.67 times 10 raised to the power of minus 11 times the mass we are looking for times the small mass divided by the two rate, which is the radius and the height above. This will give us, let's put in our calculator, and it give us 8.14 times 10 raised to the power of minus 9 m we are looking for, divided by 3.4 plus 1.7, it was 5.1 times 10 raised to the power of 6. Let's keep this one. Let's look for the second one. The second one will give us 6.67 times 10 raised to the power of minus 11 times what we are looking for times 122 divided by 3.4 times 10 raised to the power of 6 plus 6.8 times 10 raised to the power of 6, and this will give us, hope it will be the same, 1.14 times 10 raised to the power of minus 9 m divided by 10.2 times 10 raised to the power of 6. The increase in gravitational energy is 5.1 times 10 raised to the power of 8. That means we will say u1 minus u2 equal to 5.1 times 10 raised to the power of 8. And this will give us, we will say 5.1 times 10 raised to the power of 8 equal to 8.14 times 10 raised to the power of minus 9 over 5.1 times 10 raised to the power of 6 m here minus 8.14 times 10 raised to the power of minus 9 divided by 10.2 times 10 raised to the power of 6. This will give us 5.1 times 10 raised to the power of 8 equal to. Let's remove the fractions. We will now get 1.596 times 10 raised to the power of minus 15m minus 7.98 times 10 raised to the power of minus 16m. With this, m will give us 5.1 times 10 raised to the power of 8 divided by 7.9796 times 10 raised to the power of minus 16, 6.4 times 10 raised to the power of 23 kilogram. Calculate the gravitational potential. We say that the gravitational potential is work done per unit mass. That means work done per unit mass. The gravitational potential will be minus g m over r. Take note of this, minus g m over r. Gravitational potential is simply gravitational potential energy divided by the mass. Now, this will give us minus 6.67 times 10 raised to the power of minus 11, which is being given to us on the equation page, times the mass that we were looking for, 6.4 times 10 raised to the power of 23, divided by the radius of mass is given to us as 3.4 times 10 raised to the power of 6. 3.4 times 10 raised to the power of 6. This will give us 1.3 times 10 raised to the power of 7. The unit now will be joules per kilogram. 1.3 times 10 raised to the power of 7 joules per kilogram. Kindly take note of that. The satellite in B is moved to an orbit in which the satellite remains the same point above the surface of Mars. The orbit has a period of 25 hours. State what can be deduced from this orbit, the rotation of Mars on its axis. Remember, they have mentioned some things that move with the same at the points above the surface. Simply means that the orbit here is now going to be as that of the Mars. What I'm going to write here will be that Mars will take 25 hours to rotate once on its axis. That is very important because it is the period, and period is the time taken for a complete rotation. Another thing I can say is that both will move in the same direction. Kindly take note of this. So thank you for watching to the end. We will look into another question. See you in our next video.